Hi everyone, welcome back to the Solver Reading Club. It's an ongoing series where I read papers on MILP and CP-SAT solvers and discuss them in simpler terms. In today's video, we are going to look at how SAT solvers encode the pseudo-Boolean constraints. In particular, we are looking at this paper, Revisiting Pseudo-Boolean Encodings from an Integer Perspective. It's a paper by Hendrik, Jip, and Peter that was presented in CP-IOR 2025. So let's get started. We'll start with some background for the SAT solvers. Okay, so unlike MILP solvers, SAT solvers don't have general linear constraints, and they in fact don't even have general integer variables or continuous variables. So they only have Boolean variables, and we'll denote them by this thing, L1, L2, L3. So sometimes they are also called literals. That's why we are using L symbol for denoting them. And for the constraints, they have clauses. So they are basically ands of ors. So they look like something like this. Okay. So for this one is one clause, L1 or L2. This is another clause, L1 or not L3 or L4, and so on and so forth. So these are like individual constraints you can think of, and together SAT solver will try to satisfy all of them, and that's why they are basically in conjunction of each other. Okay, so that's the two major restrictions that the SAT solvers have, and we'll learn how to deal with them. Okay, so first of all, using this kind of Boolean variables and clauses, what all things we can represent. So obviously we can represent some Boolean functions as it is. So for example, or, and not, those are directly supported because the clauses, the way they are represented, they directly have those constraints inbuilt them. Besides them, we can also write XOR constraints like this. So for example, if we want to write L1 XOR L2 equal to 1, so this is how we can write it. We can write these two clauses, which is L1 or L2 and not L1 or not L2. So when L1 and L2, both of them are 1, so then this clause will be false, and therefore the formula will be false. And when both of them are 0, then this clause will be false, and therefore the formula will be false. We can also represent implications. For example, if you want to write L1 implies L3, then this is how we can do it. We can write L3 or not L1. So either L3 is true, or if L3 is false, then it must imply that L1 is also false, right? So that's the way of writing implications. So we can also write L1 and L2 implies L3, the same idea. We can say that either L3 is true or one of these two, L1 or L2, is false. So that's this clause. So in general, since we have or and not gate, we can make NOR gate, or and not gate, we can make a NAND gate. So those are universal gates. So pretty much we can represent any Boolean function using this kind of clauses, right? Of course, it matters how we actually encode them, and so that's what the focus of today's video is. So in particularly, we are focusing on a specific type of Boolean constraints, which are called Pseudo-Boolean constraints. So what is that? So that's basically, they look like linear inequalities. So these are the literals, LIs. They have some coefficients, QIs, and we are summing them, and that entire sum should be less than equal to K. Okay, so this is one of the example, which is 2L1 plus 3L2 plus 4L3 is less than equal to 5. So this is not in the form of clauses, so that's what we are trying to do. But before we jump into that, let's make a couple of things clear. So first of all, this pseudo-Boolean constraints, this left hand side is a sum of or weighted sum of literals. The right hand side is a constant, and this can be either less than equal to, or greater equal to. But to make things simpler, we will follow a standardization. Okay. So in this standardization, we will always say that we are dealing with less than equal to constraints. All of these QIs are positive, and K is also positive, right? So if any of this QI is negative, then we will use its complement literal instead of that. So, and we can change it into a positive coefficient. And if all of these are positive and K is negative, then that constraint is trivially not satisfiable, so we will not discuss that. So k, we'll assume that it is also positive. Okay, so how do we encode them? So there are a bunch of different ways of encoding them. So let's take a look at them. So for the first encoding method, we are going to generate this kind of a tree-like structure. Okay, so these leaf nodes will represent these terms. So we have 3 leaf nodes and we have 3 terms. So the first leaf node, which is node number 3, that represents this term 2L1. So I have a Boolean variable z32 for that. So 3 is the index of the node, which is this one, and 2 represents what could be the possible sum up to this point, right? So if this literal is true, then the sum up to this point will be 2. Otherwise it will be 0. So 0, we will not create a separate Boolean variable for this, because here there are only 2 possibilities. Okay. Similarly, for this node, node number 4, that will correspond to this term 3L2. So we will have a variable z43. This node number 2 will actually combine these 2 nodes and represent these 2 terms together. Right, so here at this point we have 4 possible sums, 0, 2, 3 and 5. Right, so we have one Boolean variable for each of them. So right now I'm just describing what Boolean variables we will use. I haven't described what will be the exact clauses. Right, so we will discuss that in a minute. And finally we have this 5 that will correspond to this 4L3 term, and this 1 will combine everything together and it will be the entire left hand side. So here there are many possible sums. So that is 0, 1 is not possible because none of the coefficients are 1. We have 2, 3, 4, 5 and 6. So notice that sum higher than 6 is also possible. For example, if L2 and L3 are true, then we can have sum 7. If all 3 of them are true, then we can have sum 9. But we don't have Boolean variables for that, and that's because of this right hand side. So the right hand side is 5. That means anything 6 or above is kind of equivalent for us. So they are all basically failing the constraint. So all of that, all the sums 6 or above is represented by this one Boolean variable z16. Okay. Right. So now let's take a look at what will be the clauses that we can use for connecting these different Boolean variables. Okay. So for the first clause, we'll say that at the root node z16 is false, because we want to satisfy this constraint, obviously. So that will be on its own its clause. And for the other nodes, we can just simply write this kind of clauses, right? So this is saying that z32 and 43, if this one is on and if this one is on, then at this point of time the sum will be 2 plus 3 5. So z25 will be on, right? So that's what this clause is saying. So in general we can have some clauses like this. So at node x the sum value v clause v Boolean is on, and at node y the sum value w is on. So if these 2 are on, then that would imply at the common node, ancestor node, let's say here, the minimum of v plus w, right? So in this case 2 plus 3 is 5. So if 5 is smaller than 6, so that will be on. Or the right hand side plus 1, in this case it is 6. So whenever the sum exceeds 5, that's what we will use it, right? So for example, if z25 is on and z54 is on, so that would imply that z16 is on, because we don't have z19. Okay. So obviously for the leaf nodes we need something more. So for example, in order to trigger z22, we need to make sure that z43 is false, right? And z32 is true, right? So those are some extra clauses, but you get the idea of how we can use these Boolean variables to write this kind of clauses and feed it to the SAT solver. So obviously this is not in the regular clause format, it's not and or for, but we already saw that we can represent implications in the normal clause format, right? So that's what I'll be using for now on. So this entire method is called Generalized Totalizer. So that's one way of encoding Pseudo-Boolean constraints. right? So let's now take a look at another method. So here we will use binary variables again, but this is what it will represent. We'll create Zij, and that will be equal to 1 if sum of first I terms is greater or equal to j, right? So we will have Z1j, Z2j and Z3j, and j will run from say 1 to 6 or 1 to 5, or maybe even 0 to 6 or 0 to 5. Okay, so in mathematical terms it will look something like this. So Zij equal to 1, that basically means I'm summing from 1 to I terms, first I terms, and that partial sum has to be greater or equal to j, not equal to j but greater or equal to j. So this is called sequential weight counter, right? Now let's take a look at what will be the exact clauses in this representation. Okay, so the clauses will look something like this. So first one is, there are 4 different types of clauses. Okay, so the first one is Zi minus 1j. So if the sum of first I minus 1 terms is greater or equal to j, then obviously the sum of first I terms is also greater or equal to j. It can be more than j, but we are using greater or equal to, so we are fine. And this is only true because all the coefficients are positive. Okay. Next we have, if Li is true, then Zij is true for j between 1 and qi. So for example, if L2 is true, then sum of first 2 term has to be greater or equal to 1, it has to be greater or equal to 2, and it has to be greater or equal to 3. So that's what this is saying. The third one is if sum of first I minus 1 terms is j and Li is true, then sum of first I term has to be equal to j plus the coefficient of Li, which is qi. So it is j plus qi. And we'll only use this clause as long as j plus qi is less than or equal to k, the right hand side. So in this case it is 5. So we'll use it only when j plus q is less than or equal to 5. So what happens when this is not holding? So in that case we will have this condition, which is sum of first I minus 1 term is k plus 1 minus qi, right? So in this case, if Li is true, then the overall sum will be k plus 1, right? And that is making this constraint infeasible. So we will put a negation at the top of it, right? So obviously all of this needs to be converted into that standard clause format, but we know how to do that. So this is sequential weight counter. And now let's look at another method, which is this one. So we'll start with a root node. We'll again make a tree-like structure. We'll start with the root node. At the root node, we will look at the first term, and there are 2 possibilities here. So L1 can be true or false, and that will represent 2 possibilities for the sum. So here we have sum is 0 or sum is 2, right? So this first index is the literal index, which is the 1. Okay, and from each of these possibilities we have 2 more possibilities for the second literal, which is L2. So if L2 is true or false, depending on that, we have 4 more possibilities, which is the sum can be 0, here the sum can be 3, sum can be 2, or sum can be 5, right? So they are coming from specific cases, so not in general, but so sum for 5 is only possible, it's only reachable if we are at Z12. Okay, so that's how we do it. Notice that in this case, if I had this coefficient 2 instead of 3, in that case we'll have only 3 possibilities. The sum could be 0, 2 and 5. So in that case we would merge these 2 nodes, 4 and 5. Okay, so we can basically compress this graph if you need to. Right, and for the third layer we will not create all possibilities. So at this point of time, this is the last term. So depending on whether it is the L3 is true or false, so we would already know whether this constraint is feasible or not. So we'll only have the 2 nodes at the end, which is either it's feasible or not feasible. So this is representing feasibility, this is representing infeasibility. So if we are here at node 3, the sum is 0, then no matter what the L3 takes, If it is true or false, it doesn't matter. We will always remain feasible. If we are at any of these other nodes, then depending on, so if L3 is true, then we will reach infeasibility, but if L3 is false, then we will reach feasibility. So that's called our decision diagram. And how do we represent the clauses? So obviously we will say that we don't want infeasibility, so we will say that this Boolean variable z infeasible is false. And for the other ones, we can just write clauses for these individual links, right? So for example, this clause z10 and L2 implies z23, it is precisely encoding this link. So if we are at z10 and L2 is true, then we will reach at z23. So that's what this clause is saying. Okay, so this thing is called binary decision diagram, BDD. So that's these are the three major ways of representing pseudo-Boolean constraints. So there are probably more than these three methods, but we are going to focus our attention on these three ones. Right, so now let's switch context a little bit, and now let's talk about integer encoding. Right, so we don't use SAT solver as it is all the time. So sometimes we use SAT solvers as the backend of a CP solvers, and in CP solvers we have integer variables. So if we are using a SAT solver as the backend, and if we have integer variables in the CP solver, then we need to encode these integer variables into a bunch of booleans and a bunch of clauses, right? So how do we do that? So there are many different ways of doing that. We are going to look at two of them in particular. So the first one is called order encoding. Okay, so how does that work? So we are going to create Boolean variables which represent this thing. So here we have x1 as our integer variable, which is taking this values 0, 1, 2, 4, 5, 6, 7. 3 is not present, but all the other values between 0 and 7 are present. So we'll say that x1 is less than or equal to v. So that is one Boolean variable, and v can be all of these values, right? So for example, we'll have x1 is less than or equal to 0. That's one Boolean variable. This is second Boolean variable. This is third Boolean variable, so on and so forth. Okay. So obviously there are some implication chains for this Boolean variable. So for example, if x1 is less than or equal to 0, that also implies that x1 is less than or equal to 1. And x1 is less than or equal to 1 would imply that x1 is less than or equal to 2. Right? So this is a standard implication chain. And we can also do slightly differently, right? So for example, some SAT solvers would create Boolean variables for greater or equal to inequalities instead of less than or equal to, right? So there will be x1 greater or equal to v format. But here we can also do it, represent it using this format. So for example, if we want to say that x1 is say greater or equal to 2, then what do I have to do? I will have to say that it's a negation of this variable. So if x1 is less than or equal to 1, not of that is basically saying that x1 is greater or equal to 2. If you want to do strictly greater than, then that also is possible. We'll just first convert it into greater or equal to using the next domain value. So for example, if you want to say x1 is greater or equal to strictly greater than 2, then that basically means that x1 is greater or equal to 4, and that basically we can do it by saying that not of this one, right? So that's how we do it. We can obviously represent this kind of holes in the domain. So for example, 3 is not present, so that also we can do it using this kind of implications on these Boolean variables. So that's one way of encoding things, which is order encoding, and it's kind of very natural way of encoding things. It leads to very natural propagations. But there is another way of encoding things as well. So it's called binary encoding. So here what we are going to do is we are going to use the bit representation for these values, right? So we'll say that if the kth most significant bit is 1 or not, and those are my Boolean variables. Right, so we are representing here 0 to 7 as my initial domain. So that means we need 3 bits. So here all of my domain values are non-negative, but if we have negative values as well, then we can use 2's complement for representing this integer variable. Right, so that the most significant bit will be the sign, and then the rest of the bits will be used to encode the particular value. Okay, so here for an example, we need 3 bits, and depending on whether they are on or off, this variable can take a particular value. So for example, if the 0th bit is on, first bit is off, and the second bit is on, then that would mean that x1 is equal to 5, right? So again, like all these comparisons and other things can be done just like in the order encoding as well. It's a bit not trivial, but it's possible, very much possible. And we have to do some kind of lexicographic comparison using these 3 bits, but it is still possible. This doesn't lead to that natural propagation, but the major advantage of this way of encoding is that we are using significantly fewer Boolean variables, right? So here we just need these 3 Boolean variables to represent all of these values. Right, so now let's switch contexts again, and now let's talk about the ternary constraints. So what are the ternary constraints? So we have 3 integer variables, x, y, and z, and we are particularly interested in this thing, which is x plus y, either equal to z or less than equal to z. Okay, so we want to represent this sum, and we are going to use this method for representing the sum, which is called ripple carry adder. Okay, so for this we are focusing on the binary encoding of the variables. So how do we do this? So we do it using how we do the bitwise arithmetic, right? So for example, we need 2 things. So obviously we need to note that whether the kth bit for z variable is on or off, and that is basically saying that if the kth bit for x is on and kth bit for y is on, right? So we XOR these 2. On top of that, if we are not looking at the smallest significant bit, then we also have the carry coming from the previous bits addition. So that is represented by this ck minus 1. So that's one part of the summation, and obviously we need to figure out how to set these ck variables. So that is the carry part, and that can be done again using this kind of formula, which is the kth bit for x, kth bit for y, and the previous bit carry. If any 2 of them are 1, then we'll set the carry to 1. So again, this is not a constraint in a clause format, but this is kind of easier to write it in a set of clauses, right? So we have to write 3 to 4 clauses to represent that. It kind of looks like a pseudo-Boolean constraint, but it is not, because in this case it's a simpler case of a pseudo-Boolean constraint because all the coefficients are 1. So the corresponding clauses are very easy. So we just need 4 clauses and we can represent this very easily. Okay, so this is how we can basically represent this kind of a constraint whenever we want to write x plus y is equal to z. This is we'll do for all the bits for z and all the carry bits like this. Okay, so this is when we are using this bit encoding or binary encoding. What if we are using the order encoding? So there also we can do similar things. So for example, if we are looking at a ternary constraint x plus y is less than equal to z, so my Boolean variables are of this form: x is greater or equal to v, or y is greater or equal to w. These are the form, right? So we described it using less than equal to, but here we are looking at greater or equal to, so which is kind of same thing. So whenever x is greater or equal to v and y is greater or equal to w, so that will imply z is greater or equal to v plus w, right? And we create this kind of clauses for all the v's in domains of x and all the w's in domain of y, and we put them in ands. Okay, we combine them together. So that's how we can represent the ternary constraints when we are looking at the order encoding. So we can do also equality constraints as well. We can use similar variables, but I'm not going to describe how to do that. Okay, so it's kind of obvious from this. Right, so now let's go back to the way we were looking at the pseudo-Boolean constraints. So let's start again with generalized totalizer. But now let's think of this intermediate or even starting Boolean variables and view them as integer variables. Okay, so for example, this is representing one intermediate integer variable, which is basically saying that what would be the sum for these two terms, right? So that is my intermediate integer variables. And what is this part of this subtree? So right, so this is kind of a tree which is in this format. So if I have one integer variable plus another integer variable less than equal to this integer variable. So we are using less than equal to because our pseudo-Boolean constraint is less than equal to. So we don't really need equalities here. We can just simply propagate things with less than equal to as well. So that's what we want to do. Right, so this is my first integer variable, this is my second integer variable, and the sum of these two is represented over here. We are not explicitly going to create integer variables in the SAT solver. So we are only going to view them as integer variables, right? So this is like a pseudo integer variable. So they are not really present in the SAT solvers because SAT solvers only have Boolean variables. But if we are viewing them as integer variables, then we have some freedom. So we'll talk about the advantages of looking at these variables as integer variables later in this video. Okay, so we can do this with generalized totalizer. We can also do this same thing for sequential weight counter as well. So here we created this kind of Boolean variables, zij equal to 1 if sum of the first items is greater or equal to j. And we can think of this as also an integer variable, right? So instead of creating all of these zij variables, we can say that sum of first two terms is one integer variable, and use again this kind of ternary constraints to encode the rest of the entire pseudo-Boolean constraint, right? So if you want to say this entire three terms, then we'll say that x is my sum of first two terms and y is 4L3, right? So that those are my two integer variables, and that should be less than equal to z, which is supposed to be less than equal to 5. Okay, so again we can do this with the sequential weight counter as well. And I think if we are looking at the binary decision diagram, it's kind of also the same technique. So instead of having these layers, we will have one integer variable per layer, and that would be my integer variables. Right, so what is the point of doing all this? So what's the advantage of doing all this, right? So first advantage is that we can encode integer linear constraints directly. So let's say if we are in the CP solver, so CP solver don't just have pseudo-Boolean constraints, they have integer variables, and therefore they can also have integer linear constraints. So if you want to encode those integer linear constraints, then this kind of abstraction helps, right? So we can, so one way is that we can use integer variables and any of these three techniques, either generalized totalizer or sequential weight counter or binary decision diagrams, and then use them. We can just use those integer variables directly, and then it was simply generalized to the integer linear constraints as well, right? But if you are looking at those methods in its raw format, so for example generalized totalizer, so if you want to do that, then first we need to convert this integer linear constraint into a pseudo-Boolean constraint, and then convert that pseudo-Boolean constraint into this generalized totalizer, for example, right? So that's that would lead to some level of inefficiencies, so that we can avoid it. The second advantage is again related to encoding, and here we can encode the equality constraints as well. So again, as I said, that in the standard format, the pseudo-Boolean constraints are less than equal to constraints. But let's say if we have an equality constraint, then if you are using this kind of integer views, then those ternary constraints, right? So we can use those equality formats of those ternary constraints, and we can use them directly, right? So that's the advantage for again using those integer point views. And the third and the most important advantage is we can use mixed encoding for integers, right? So if you look at generalized totalizer or sequential weight counter, so for sequential weight counter we were using zij equal to 1 whenever the sum of first item is greater or equal to j. So if you think about it, it kind of mirrors this order encoding for integer variables, right? So we are saying that the first item is greater or equal to 1, is greater or equal to 2, greater or equal to 3, and so on and so forth. And then we are basically creating clauses for them, right? So there we are stuck with this order encoding. But if we are looking at those intermediate variables as integer variables, then we also have an option to use binary encoding for them. So for example, if let's say some of those intermediate variables, right? So the domains over there in between, they get very large. In that case, it is kind of beneficial to switch from the order encoding to binary encoding. And that's what these people did, and they observed significant advantages whenever they were using this mixed kind of encoding. So they would use order encoding as long as the domain size is smaller than a particular value, and they will switch to binary encoding whenever the domain size exceeds that. So that would basically result in fewer binary variables and fewer Boolean variables, and that would lead to much better and faster propagation. Okay. So these are the major advantages. So I'm not really going to describe the experimental results for this paper. So they basically experimented on some knapsack type of constraints or some other types of constraints as well. They created the problems for that, and then they tested this methodology with some of the other solvers as well. And it turns out these advantages are kind of very important. So something that we also didn't talk about in this video is that it actually enforces better domain and bound consistencies. So I didn't really define what the domain consistency is and bound consistencies are, so I'm not really going to talk about it more, but you can obviously read the paper. So that would be the end of this video. We'll quickly conclude. So we looked at how SAT solvers work and how do we encode this pseudo-Boolean constraints. We looked at 3 different methods: generalized totalizer, sequential weight counter, and binary decision diagram. We also saw how to encode integer variables using order encoding and binary encoding, and then we looked at how to encode the ternary constraints, and using the integer variable encoding and the ternary constraints, we looked at how we can use the combination of those two in this pseudo-Boolean encoding for all of these 3 methods: generalized totalizer, sequential weight counter, and binary decision diagram as well. So how that benefits. So that would be the end of this video. I hope you liked it. So don't forget to press the like button. Subscribe if you haven't already subscribed. It helps me grow this channel, and I will see you in the next video.